Hello everyone, welcome to our talk on exercising Wraith, protecting LiDAR-based object detector in automated driving system from appearing attacks. I'm Qifan Xiao from Fudan University. In this paper, our main research target is the model safety in the mainstream automated driving systems. Most automated driving companies, such as Baidu and Waymo, will deploy various sensors on its automated driving vehicle to collect data from environment. Based on this data, the automated driving system will locate its position and perceive the driving environment at first. Then it will predict the movements of nearby objects and plan the future route of itself to avoid these objects and reach its target position. These results will be translated into a series of instruments to control the automated driving vehicle at the hardware level. Since the data collected by LiDAR is more precise and contains more spatial information, most automated driving companies will choose it as the main sensor during the perception process. However, recent works have proved that it is possible to modify the point cloud data collected by LiDAR with the support of such physical equipment. This equipment will capture the lasers sent by LiDAR and use laser transmitters to forge the reflection. Such attacks, which we can refer as appearing attacks, will inject some fake points into the collected point cloud data and fool the automated driving system to detect some inexistent vehicles. These forged vehicles usually appear in front of the target vehicle, force the target vehicle to emergency brake or keep it immobile, which may often lead to the traffic violation, the traffic jam, or even some serious accidents. We can generally describe the magic of such attacks from three perspectives: its predictability, its naturalness, and its variability. Nowadays, the mainstream automated driving system will use DNN models such as point pairs, point RCNN, and PV-RCNN to detect objects from the point cloud inputs, which means the key of the detection model are differentiable. If the attacker clearly knows the structure and the parameters of the target DNN model, he can simply apply some traditional adversarial methods such as PGD and CNW. After modeling the pre-processing and post-processing functions to deploy the attack, which we consider as its predictability. Also, such knowledge may be too difficult for the attacker to acquire. The detector can also directly copy a real vehicle with few points to attack. Such forged vehicles are more difficult for system or human to distinguish, which we consider as its naturalness. Furthermore, forging a full vehicle is not the only choice for such attacks. There also exists an attack which aims at enlarging the predict size of a real vehicle. Such attack may pose essentials as we mentioned before, which we consider as its variability. How to defend against such attack is not actually new topic. There already exist some defense methods designed in the universal way or the specific way. For example, the SRS and SOR are two representative universal defense methods. However, they both mainly focus on improving the robustness against natural noise, while its defense effect is uncertain, since it is unaware of attacks. Besides, SVF, Paro, and Shadow Catcher are three specific defense methods. However, they all mainly designed to defend against the black box appearing attacks proposed in Sun's War in 2020, while ignoring other potential attacks such as the ADV LiDAR proposed in Chao's work in 2019 and the bounding box enlargement attack proposed in Yang's work in 2021. The performance of this specific defense remain unjustified. Therefore, we analyze existing appearing attacks and we find that there are two common limitations of them. First, constrained by the physical equipment, there are only up to 200 injected points once attacked, and these points all have to locate in a limited space. Second, the attacks mainly focus on increasing the similarity of the forged vehicle and a real one in global, which means they may ignore their difference in details or in local. To make use of these two limitations, we further observe the forged vehicles and the real vehicles in the point cloud format. As the left figure shown, we find that the point density are inversely proportional to the depths for most real vehicles, while the forged vehicles usually have the lower point density and depth at the same time. As the right figure shown, the difference between a forged vehicle and a real one are larger in local, which means these attacks cannot intimidate real vehicles in local with a high quality. Therefore, based on these two key findings, we have made a multiple designs. Based on the first finding, we introduced the point depth as an explicit feature and density as an implicit feature into the input point clouds in order to modeling the depth-density relation of real vehicles. Based on the second finding, we adopt the idea of a component segmentation and the voting strategy. More specifically, we separate the detected vehicles into multiple pillars, identify whether the component in each pillar belongs to a real vehicle or not, and distinguish the vehicle based on the vote of these identification results. In general, we designed the LP, local objectness predictor, and proposed this detecting pipeline to defend against appearing attacks. As a plug-and-play design, the construction of LLP is completely coupled from the protected detector. In the first stage, we split each collected training samples into several pillars with fixed size, and label it based on the IOU, intersection of union between the ground truth and itself. Then, we acquire a point cloud data with binary label, which represents whether the corresponding point cloud is a real component of vehicle or not. In the second stage, we introduce the depth and density feature into the input point clouds in this new training set, and randomly remove a part of training samples to balance the training set. In the third stage, we finish the training of the LLP and deploy it after the protected detector to identify the separated pillar of input space. According to the voting of LLP, we can finally determine whether a detected vehicle is a real vehicle or not. We compare LLP with 4 defense methods we mentioned before, against 3 different appearing attacks on 3 different 3D object detectors. Here, we mainly show the experiment results on point pillars. We reveal that LLP are all located on the upper right part of the left figure, which means our proposed defense has more improvement on the performance and robustness of protected 3D object detectors than others. As the right table shows, our LLP needs slightly larger codes on both memory and time. However, there still exists some optimization methods such as multiprocess can further reduce its running time. And in the next part, we prove that the time overhead will not be the bottleneck of our LLP in a real automated driving system. As what we just said, we also perform a simulation experiment on LGSVL simulator. We deploy LLP into Apollo, an open source automated driving system proposed by Baidu, and evaluate the performance of it against appearing attacks. As the table shown, without deploying LLP, the appearing attack can easily fool the Apollo to detect an in-system vehicle, while deploying LLP can not only reduce the ASR of appearing attack to 0, but also lead to less than 10 millisecond calls on time during each detection. Besides, the FPS, frequency per seconds of the whole ADS, are only reduced from 29.97 to 23.54. The results also convince our previous opinion that the time overhead will not be the bottleneck of LLP. Also, there are many advantages of our proposed methods. The core part of this work is actually proposed years before, which means there are several future directions remain for this work. The first direction is that some real vehicles may be accidentally removed by LLP, which means appearing attacks are still possible to cause real-world threats to the ADS deploying with LLP. However, we also find that the most accident removal, which we refer as the FP false positives, are actually far from the adversary vehicle. Only 12.95% of FP are less than 10 meters, and only 16.53% of FP are less than 20 meters away from the adversary vehicle. Since these VFP are far away from the adversary vehicle, they can hardly affect the planning of ADS in the short term, and the negative impact is limited. On the other hand, there is a new appearing attack called PLA LiDAR, proposed by Jing in SMP 2023. This work designs a new physical equipment, which can inject at most 2,540 pounds in one frame. And we haven't evaluated our proposed method on it against such powerful attack yet. So we think the future defense should be designed both the software level and hardware level to defend against such powerful attack. And finally, as a summary, in this paper, we conclude the limitations of existing appearing attacks and propose a plug-and-play defense method, LP, whose robustness are guaranteed both online and offline. And that's all my presentation. Thank you for all your listening. For more details, feel free to scan our QR codes to read our paper or follow our research.